So I want to first confess something. I have a problem at work, and I'm going to assume that most of you at least have the exact same problem. We are processing data, and that data doesn't belong to us. And usually when you're in that situation, that data comes with strings attached, most usually in the form of massive penalties if you mess things up. So usually financial penalties, but it can be legal penalties, and so on and so forth. And of course, when it comes to that, then the topic of securing that data becomes a major area of debate and discussion. But when we look at the technical solutions to fix that issue, what you get is a kitchen sink of standards, libraries, software architectures, design patterns that are all but elegant, that have very little consideration for elegance and simplicity, compositionality. They all share one common trait. They are designed from the outside in, meaning that they try to erect these huge walls between you and the external world so that nobody can penetrate unless you enable them. That's not how we used to do. That's not how we like to do it as functional programmers. We like to design from the inside out. By the way, can you hear me if I speak here? Awesome. We like to start from a core calculus that is minimal, compositional, that displays laws and behaviors that are easy to understand, easy to aggregate into more complex behaviors. And so it's kind of an insult, at least for me, that we have to use these solutions. So if you want to start and think about a way that is designed using that kind of philosophy, then there is something that exists. It's called information flow control. Information flow control is essentially a tool where you analyze the flow of information between variables in your system, and your security policy determines which flow are valid and which ones are not. And by the way, all of these solutions that I mentioned earlier, they have one major flaw, which is that, yes, they make access to your system difficult, but if you manage to get access into your system, you can do whatever you want, and there's absolutely nothing you can do about it. Case in point, I'm sure you've read in the news, massive leaks of personal information leaked by your favorite social media platform, a utility provider, a secure password manager, and so on and so forth. And I can bet that most of the developers who work there would have said that their system is secure, but they clearly aren't. So information flow control is actually something that is extremely easy to implement, especially for people like us, and especially in the context of the FX system that we know and love, because FX systems like ZIO, KIO, ZPure, CATS-Effect.io, and so on and so forth, they're all about very precise flow control. So it sounds like a match made in heaven, and just why not go and see how we can plug information flow control on top of it. Actually, we don't have to look very far, and I don't claim to bring anything new to the table. This has been already done many times. It's just that it's not very well known for some reason. And most of the code that I'm going to share is taken from that paper, which I invite you to read. Very informative. But let's first try to build an intuition as to how information flow control works. It essentially attaches labels to data, And these labels have specific properties. Effectively, there exists a relation, a binary relation, that determines if two labels are, one label can flow to another label. That flow relation effectively determines if information can go in, from one data source to a data sink. And so here is an example of a very simple security lattice made of 3 levels. Now, the labels themselves do not mean anything, but the flows do represent where information can go to. Intuitively, you cannot take a secret and leak it to the public, for example. That wouldn't be a valid exchange of information. So let's see what the execution of a program in that context would look like and how information flow control works under the hood. So the gist of it is that you have a piece of state that you maintain in your computation made of 2 things. The first is the label of your computation. That label is said to be floating because it may change over time as you execute specific workflows. And you also have a security clearance. So that's a label that determines like the top level access control, top level access that you can exercise. So here, this workflow, we start with essentially the full gamut of access control, which is that your floating label is starting at the public level, and your security clearance is top secret. Bold is for clearance, and italic is for floating label. So let's go through it. You start your workflow, nothing happens. Then, using my own version of Quill, which is using security labels under the hood, I'm trying to access a secret data source. And when I want to read secret data, to which the secret label is associated, I need to check if the security label is between my floating label and my clearance. So in this case, secret is indeed matching that invariant. But the other thing that I need to do is when I observe that data, which is when I select it, I need to raise my current label to the level secret, meaning that at this point I cannot go back to public anymore. I have access to secret data. Next, I just do some computation of on those results. Nothing happens. It's a pure computation. I'm not exercising any privilege here. But then I want to store that result to a top secret data source, a data sink. In that case, I'm not really observing data. I'm storing data into another data sink. So I don't need to raise my label, but I need to make sure that the sink to which I'm storing data, its label is also within between my security label and my security clearance. And in that case, since a label flows to itself, it does much. That's the happy path. Now let's look at what a scenario in which we have a security breach looks like. The first one is, let's say that, again, I'm reading secret data. I have raised my label to the secret level. But now I want to insert that data into a public data sink. Now, that's not going to work. And the reason why is because the public label is outside of my boundaries. I have a security breach. My program needs to bail out. It's not going to happen. Second scenario is, let's say that my security clearance now is set to secret instead of top secret. Again, accessing secret data is fine. Raise my label. But now I'm trying to access top secret data. I don't have clearance for it. My computation bails out, fails miserably, and I avoid a potential data leak. Right, so that's pretty much how it works. Now I'm going to show you the implementation of it, which is very, very simple, but I have some good and some bad news, so you choose what should I start with. Bad news? Good, because I was going to start with the bad news anyway. Okay, let's get down to it. Come on, it's just one parameter. Doesn't hurt. There's only just 1,000 libraries to update, right? The only problem is that that parameter is invariant, and it may have a little issue with type annotations. But bear with me for a moment. Let's look at the API. So why do we need a parameter in the first place? Well, the reason is because there's not one type of lattice, of security lattice. There are many lattices that exist. Perhaps you have one in place at work. Everyone is different in that case. And so the only thing that matters is that it's a whole class of data types that have specific properties. One of them is that, it's a lattice, so you need to be able to sort of join two labels together, or compute the greatest lower bound. That's the definition of a lattice. But the most important property is that binary relation, which is the flow property, which I call less than or equal, because it's a partial order. Once we are equipped with that, as I said, we need to store in our computation the current label, the floating label, and the security clearance. And as we execute a workflow, that security clearance and label may change. But they may change only in such a way that the invariant is kept always. So, for example, the label can only go up, and the clearance can only go down. It can never go up. And one thing that is extremely useful as a data type in a security context is where you have, let's say, a component that is executing some piece of shared logic. So let's say that you are, aggregating data coming from all of your clients. The only thing that you want to avoid is to leak, data from one tenant to another. That would be catastrophic. And so typically what you want is restrict access to the data itself. But you still want to be able to process it in some way. So the metaphor is that you have a box that is sealed. You have many boxes. Each box contains client data. You can do whatever you want with these boxes, as long as you don't try to open them. If you try to open them, then you're going to have a security breach. And yes, so the action of opening the box, because the box is labeled, you need to, if you want to unseal it, which means that you want to observe the data, you need to try to raise the label. So you compute the least upper bound between your current label and the label on that box. And if that current label is, matches your system boundary, then you can proceed with the computation. Otherwise, you have a security breach and you die. And of course, if you want to create such a box with a specific label, it wouldn't be logical that you could create a box with any label. That label needs to be within your label and your clearance. Otherwise, of course, you could just mess up your system, introducing top secret data that could do damage to your company. Once you have that core foundation, then it starts to spread among your, among the ZIO library, almost like a virus. It's very easy to build, a ref that is labeled, which you can access only if you have clearance for it. It's very easy to build queues that are secure, promises, trefs, and so on and so forth. Streams, sinks, etc., etc. And of course, why not stop there? In fact, I would argue that probably ZIO is it's probably the best library that has the capacity of taking that idea and spreading it among its whole ecosystem in just a minor version update. An example would be, as I said, Quill wouldn't be very difficult to extend Quill with a context that enforces tenancy isolation with whatever strategy you want, either row-level security or even database isolation, and so on and so forth. Sources of data like DynamoDB, Kafka, the file system, of course, they can all be labeled very easily. And ZIO HTTP, of course. I've just been through the exercise of setting up the authentication and authorization framework at my company. It was a very painful experience, again, using all of these kitchen sink technologies. Not something I would recommend, but a labeled root gives you most of what you need in a very elegant, very small, very easy, very composable fashion. Right. So yes, that's the theory. That label class of data type that can accommodate any use case. But it is indeed very annoying that we need to add that fourth parameter to the ZIO data type. I don't see this happening anytime soon, so we need to make some compromise. And the good news is that the Scala language is a language where you can cheat, given how versatile it is and given that it tries to be everything to everyone. So it turns out that in my use case, in my own personal experience, there's a very specific type of label that I need. It's a label that allows me to identify mutually distrusting entities, right? So we have multiple clients, and then these clients, by default, do not trust each other. And so everything after that follows naturally by that simple property. The same authors came up with an encoding of that, of a label that allows you to encode that in a very, very elegant fashion. And I'm going to use that as a concrete instance of label that is going to be the only one that my library is going to deal with. But as I said, should you wish to create your own version of a label, I'm still going to allow you to do that. The only thing is that I want to ditch the implicit the type class machinery, and I'm just going to use inheritance instead. I think it's an acceptable trade-off. But here is the data type that I'm talking about. A label is made of two sets of principles. The first set is the principles that are authorized to look at the data, to observe the data. The second set of principles is those that have the permission to update the data, to write, modify, or author the data. How do we combine these labels together? Well, if you want to take the upper bound, it's very simple. The observation is made more complex in a sense that if you have data that belongs to two different parties, or that is shared between two parties, you want the endorsement of these two parties if you want to observe the data. And that is the AND operator. And the integrity is the opposite, because as you combine these labels together, you want each party to be able to modify the data. And the lower bound is the opposite, which is that if you want to send the data to each party individually, they can either or can observe the data, but both need to endorse any updates to the data. Now, the flow property is a simple Boolean formula, which says that if you want to send data from one source to a sink, The sink must have a label where the read side, the observation side, the observation constraint is at least as powerful as the one from the source, which is to say that you cannot lose any constraint on the read side. And for the modification, it's the opposite, which is that you may effectively restrict access as you progress through your computation. A principal is just a set of principals. So a principal is just Alice and Bob. It's the name of your service. It can be a component within your service. Doesn't really matter. And this weird encoding is just because they are encoded as a Boolean formula expressed in conjunctive normal form. But it's just a Boolean formula. And just a few examples of principles and how they can be combined together. So here we have user Alice, and presumably every data that comes from Alice will be labeled with Alice as the author, so who has read access, and as the one who can, of course, update that data. Same for Bob. And then you can combine them together, as I explained earlier. So now that we have gotten rid of that type parameter, we can have a fiber ref, which just is going to store your state, so the floating label and the current clearance. And the thing is that if you know anything about fiber ref, you know that when you join a fiber, there's you get to make a decision as to how the values get combined together. And you can see here that I'm discarding the value coming from the fiber. I will explain why later. There's just a few combinators that are useful for outside usage. The first one is essentially restricting write access. So just as I explained in my example, if you want to use a label, you just need to make sure that that label falls within the boundaries of your labels. If you want to observe data, however, you need to raise the label to the upper bound of the current label and the floating label, and then set that label as in your state. And if you want to update data, you need to do both, essentially, because updating implies that you're reading data. And yeah, if you ever reach a point where your security policy is broken, it's usually a bug in your system, a defect in your program, or in your conception of the program, which is why in my library, breaches are considered as defects. So you cannot like recover with map error and stuff like that. It wouldn't make sense, in my opinion. Once you have that, yeah, again, as I said, these things spread very easily, but I need to focus on one thing, which is the actual bad news. The fork semantics cannot be used as is. So if you want to have a system that is secure, you cannot just fork fibers. And the reason being that your fiber can be joined by another fiber which has a security clearance that does not allow it to observe the result of the joining of the joined fiber, right? So you need a new fork combinator that will give you that guarantee. And unfortunately, the core fork combinator cannot be updated to accommodate that need. So I create my own version of fiber and introduce a new fork combinator, which is going to be essentially just making sure that first the label I want to fork with matches my invariant, and then just going to fork the computation and wrap it inside my fiber. And oh, I think that's all right. Forgot one part, which is that if I want to observe the result of that fiber, either using a wait or join, then at that point I can guard the observations or the observation of that data, and again, die miserably if the joining fiber is trying to read something that it doesn't have access to. And that's pretty much it in terms of the content of the library. It's a very small core, but I was very surprised in, discovering that even with like 2 or 3 combinators, you get something that scales very elegantly and that is secure from the inside out. So if you manage to design your security lattice in a reasonable fashion, and you isolate your components, again, you need to think a bit about that, but the way you combine your fibers and so on and so forth, so that the data flows in a secure fashion, and your floating label never breaches, then you get a system that is essentially rock solid. It can never leak data anywhere, and you don't need to use any of these ugly technologies ever again. That is it. I don't know if you have any question, but I'm going to make the code public at that handle. And of course, if you have discovered that bug, you get a drink from me. Thank you.